Yes, thank you very much. First of all, I would like to thank the organizers for inviting me to present our results here. I mean, it's a very privileged location. I'm really enjoying the meeting. And I have to say, especially many thanks to Colette for introducing the topic in such a wonderful way that the stage is set, and I don't need to give too much of an introduction. I would like to give you a small overview of what we find with our JWST GTO team that is looking at a number of these planet-forming disks. And this is together with the MINDS team. The PI is Thomas Henning, but Evin is also part of the team. And I would like to give you a very brief motivation for why I think this is interesting. We talked on the first day a lot about exoplanets, and so we know these exoplanets are forming in these disks. I think we also have quite some evidence by now that at least the first stages of planet formation have to happen very early on. We heard that earlier from Lucas as well, advocating it. You know, maybe we should look at class 1. But certainly looking at class 2 disks, we know that the planet formation process has not yet finished. I mean, it is supposed to be ongoing. For example, if we look at terrestrial planets, we think that Earth accumulated about half of its mass very late, so more than 4.5 million years after formation of the solar system or the sun. And so that means when we look at these disks now in our sample, and we call them class 2 disks, we heard this morning the definition of a class 2 disk being like there's no surrounding material anymore, so we have a clear view of the disk. That is an age of around, say, 1 to maybe up to a few million years at most. And so actually we are looking at a phase at which planet formation, terrestrial planet formation, should be actively going on. We also have, I think, quite some observational evidence that transport processes happen, such as the radial transport that Colette introduced. And we also know from observations, as she showed, that planets can carve gaps in disks. And yes, we've seen them at large distances using ALMA, which observes the outer disk. But in the inner disk, we have very little possibility to directly image that substructure. If it's within a few AU, for example, it will not be easily seen from the ground. I mean, we would need interferometers, and Matisse is one possibility. We had media in the past. We have gravity now, although it focuses more on the very inner disk, but interferometers are then our best bet to get to that inner disk structure. Or we use JWST MIRI, and then we use the spectral information to actually tell us about the possibility that such substructures exist. And so an interesting thing I would like to point out here is that these disks are layered structures, and Colette showed that very nicely in her talk, that there is probably a kind of different radius at which each molecule may preferentially emit, simply because each molecule has its own substructure, its own excitation properties. But from the chemical modeling aspect, we also know that there's a vertical layering. There are simple molecules like OH and CO, which tend to form very close to the disk surface, and other molecules that need more and more steps to form and to assemble, subsequently form deeper and deeper into the disk. And so this is something I will come back to. Now, of course, we are not starting this whole process out of the blue. I mean, we're building here on the fantastic heritage of the Spitzer Space Telescope, and especially also people like Klaus Pontoppidan, John Carr, Jonah Jeter, Ilaria Pascucci, who worked enormously on this data. And I think we have a wonderful set of major molecules already that we knew would be in these disks, like water, for example, OH, CO, CO2, HCN, acetylene. And so what we are actually hoping for, of course, is to now, with increased sensitivity, to see many more of the minor species, to see isotopologues of these. And there's a very interesting dichotomy that has been found by Ilaria Pascucci already in Spitzer times, and that is a dichotomy between stars that look more like our sun, like maybe half a solar mass, and these very low mass stars. And then we are talking about a tenth of a solar mass as a central star. And the dichotomy shows up when we compare, for example, HCN and acetylene. So they have very different ratios in these two systems. And the other aspect, and Colette already mentioned that, is that these very low mass stars sometimes seem to have very little water. So they seem to be very depleted in oxygen. Now, this was the basis for us to define our MINDS GTO program. because we wanted to go, especially for the minor species, as a function of time and spectral type, using a large sample of this. We wanted to look at the radial distribution of polycyclic aromatic hydrocarbons, but also the mineralogy, the iron content of dust grains, and especially, and we heard about that in the introduction before, to try to quantify the role of transport processes. Because if we bring together the picture from ALMA, which observes the outer disk, with the near infrared that we have from the ground, and now the JWST mid-infrared, we should be able to actually understand at those different wavelengths what the elemental ratios in the gas are, and then make the connection to how efficient any radial transport processes may be. Now with that, let me introduce the MINDS team to you, and I have to say a really big thank you to all the MINDS team members, because without the dedicated, tremendous effort on doing the data reduction, developing additions to the standard pipeline, and dealing with our sometimes very interesting way of taking observations, this would not have been possible. So really a big thank you also to all the teams who put together JWST, because it's an amazing journey to look at that data. Stunning, absolutely stunning. So this is what we do in the MIRI mid-infrared disk survey. It's about 125 hours of JWST time. I didn't put that here, but the main bottom line is we have about 50 objects, and we also do some coronagraphy. We have some very interesting sources like TW Hydra, PDS70, and HD 169142, which may actually show already evidence of planets either having formed there or forming. And I want to add that our program is about 95% complete. We are only missing 2 objects at this stage. So we really have a ton of data to look at. And this is the basic message I want to get across. I think Colette already made that point, but I think we cannot stress this often enough. As we look at all these objects, I would say we do not find 2 disks that look alike. And this is a compilation from 2 papers we had in the Faraday discussion earlier last year by Evine van Dissek and myself, where we showed a little bit the spectral region around the acetylene band on the left, and then the more water CO2 band on the right. And the top 3 objects are T-Tauri stars. And the bottom one, or the 4th row actually, is a very low mass star. And then the bottom is SLAB models that show you at which wavelengths you should expect certain emissions. And I absolutely second the point that we should agree on a color scheme here. I think everybody agrees water is blue. So all the blue lines you see there are actually from water. And the green one, around 15 micron, is a very strong feature of CO2. And now coming back to my message, searching for the more rarer species, for example, in GW Lupi, which is the 3rd row that you see here, we detected for the first time the isotopolog 13CO2, but you also see indicated the hot bands that we detected for the first time. Those were shown to be, that they should be present in work by Arthur Bosman, but it's absolutely great that we now see them. And I have to say that a lot of the diagnostic, a lot of breaking degeneracies in the modeling comes from actually seeing those minor species, seeing the weaker lines in those molecular features, and especially also due to the fact that we now spectrally resolve at least the Q branches. We do not spectrally resolve individual lines of the P or R branches or rotational lines of water, but we do resolve the Q branches, and they have very important information about the temperatures, for example, of these molecules. Now looking at the 4th row here, the very low mass disk, you see a profound difference. I mean, there is no presence of water in this disk. This is J1605, a paper published by Benoit Tabone very early on. But you see how rich this spectrum is, and that actually when you look at the left column, where we focus on the acetylene region, for the first time we detected the isotopolog 13CCH2, which is like a shoulder on the Q branch. And so we see an immense diversity from source to source. It's a truly rich data set to look at and to model. And I will come back to that in the next slides. Let me highlight also one individual target, TW Hydra, simply because I worked on it myself together with Matthias Samland in Heidelberg. And it is a very unique object. First of all, I mean, it's the closest planet-forming disk that we know. We see it almost face on. But also because we detected two molecular ions. There's HCO+ that we see on the left, and that had been seen earlier with Spitzer, but it was an unresolved Q branch. That was a paper by Joe Najita. And now we see the Q branch actually spectrally resolved. And then on the right-hand side, we see CH3+. And this is what Olivier Bernet showed earlier this morning. He detected it for the first time in the PDRs4All program. And now we see it, but look at how weak that feature is. I mean, we really have, at least in that wavelength band, an incredible signal to noise as well. And only because we have such an exquisite signal to noise, we can see this very, very weak hint of a Q branch of that CH3+. So it is a firm detection, but you see how difficult it is to pull it out. And so based on that, I would also like to reiterate how important it is to work with molecular chemists together with people who can make theoretical predictions. Without the molecular data, which has been compiled by Shangala et al. 23, and also without the work that Evin made available to us from Frank Helmig's PhD thesis from '96, we wouldn't have been able to plot lab models for these molecular ions. And so there's a whole lot of work still to be done here. And just to show you a little bit what we can do, we can, of course, do forward modeling. So we can say, well, we understand to some extent what the structure is of that disk around TW Hydra. And it's very intricate because it has an inner disk, which is a little bit more depleted. And then it has an outer disk where we have more material. And you see in the left-hand side, the column density as a function of radius. And at around 2.4 AU, we have a strong increase in the amount of material. And I think it is exactly in that kind of inner rim of the outer disk that these molecular ions can live very well, because they have the right temperature and we get the right emitting area out to make them visible in the spectrum. Now let's look at individual targets one more time. There's the example of EX Lupi, which is a paper published by Agnes Kosbal. It's also a T-Tauri star, and you see here the sum of all the SLAP models. SLAP models are actually these very simple models where we just say, what if all the molecular, what if all the molecules are in a single column with a certain emitting area, and they are all at a constant temperature, and then we can work out what kind of emitting area do we need in order to generate the amount of emission, and the temperature gives us kind of the shape of the Q branches, just to give you an idea. And we can do that molecule by molecule individually. And then we learn for each molecule about the emitting conditions, the excitation conditions. Now, there are also much more complex forward models. We call them 2D thermochemical disk models. And they are much more difficult in the sense that you do not have these kind of
that gives us two
single
more
free
weeks
parameters
to iterate and tweak. Okay.
Yeah. So,
okay. So you do not have just like 3 free parameters. In fact, you have a lot of free parameters, but the molecules are sitting wherever the chemistry predicts them to sit, and there's radiative transfer involved, etc. And I think it's absolutely fascinating to see that we can use these forward modeling now together with evolutionary algorithms that actually crawl through parameter space to find a best fit to the complexity that we see in these JWST observations. So this is just one example done with our thermochemical disk model code CODIMO. Now, to move to the very low mass objects, and this is these are results that are not yet published, so please don't take pictures, don't tweet it around. This is work by Aditya Rabavi, a PhD student of mine and Evin, and we have gone through the spectrum and identified all these molecular features. I mean, it's absolutely stunning because we have lots of quasi-continua. This is not underlying dust producing a continuum, but it is really gas emission. So we see here the methane emission at short wavelengths. Then you see C2H4 doing its low vibrational emission. There is C2H6, very distinct features. As we move on, we see the acetylene I mentioned earlier together with the isotopolog, but there's also HCN emitting. Then, of course, fascinating benzene. It's the largest hydrocarbon we've seen to date. also with a wonderful quasi-continuum there. It's not dust emission. There's CO2, so that is coming back to the question. Yes, we do see CO2 in these disks, and some of them even CO. But there's all these molecules here. And let me just end a little bit by saying that we are starting to understand where those molecules are coming from. Again, we can look at the chemistry in our disk models, and we can study, for example, how would the chemistry look like if we have a normal canonical carbon to oxygen ratio, and then all these hydrocarbons would actually sit below a tau is 1 line, and they pile up there, but they would probably not be visible to us. But if we increase the carbon to oxygen ratio to 2, all the molecules that we have seen in the JWST spectrum, they pop up in the models. They all sit in the surface. So all of them that you see here are actually observed. But on top of that, we can predict which other molecules we also have in the models that we should be able to see, and we still have unidentified features. So let me come to the conclusion. What are actually the next steps? So this is shamelessly taking a figure from Anna Miotello's PP7 review chapter and adapting it to my needs. So you see on the right-hand side, this kind of layered structure. And actually, we have all these complex processes now because we may have transport processes that alter the carbon to oxygen ratio as pebbles are drifting into the disk. And as we cross the various snow lines, we change the carbon to oxygen. But this is only part of the picture, because what we also have is physics, chemistry, and radiative transfer. If we put a planet in there very close in, it will carve a gap. And maybe it takes out some of the molecular emission that we should be seeing. And so it will definitely alter how the JWST spectrum looks like. And to conclude, I think what we need is really large statistical samples of disks, because what Colette said about the stochasticity, I completely subscribe to. I do think, apart from the well-known axis of exploration, there is an element of stochasticity in the type of planetary systems that we form and when they start to form. And so we need hundreds of objects with JWST to be able to make sense of this. And more importantly, we need a consistent single framework, because the outer disk is showing something which is not independent of the inner disk. And so we do need to bring together the ALMA data with JWST in order to understand what we see in these disks and how it links to the composition of forming exoplanets. Thank you.